All right, good morning, good afternoon, good evening to everyone. Welcome to another session on the Digital Color Management Fundamentals brought to you by Datacolor Academy. Today with us is our colors expert, Ken Butts, who's going to be talking about getting the most out of your graphs and on-screen color when you're evaluating color quality. So Ken, I'm going to pass it over to you.
Thanks, Chen, and again, welcome everyone. It's a pleasure to be back with you. Hopefully you've had an opportunity to review the 2 sessions we've recorded so far using Datacolor TOOLS software. This is a continuation of those sessions. And today we're going to be talking, as Chen mentioned, about how to get the most out of graphs and on-screen color with your color management software. As before, we're going to be using Datacolor TOOLS software. Some of these principles will apply regardless of the program you're using. But if you are using Datacolor TOOLS, this will serve as a good training session for you, as well as giving you some practical tips on how to use some of the more advanced capabilities of the Datacolor graphics functions within Datacolor TOOLS. So in our previous sessions, we talked about tolerances, we talked about configuring the screens. So hopefully you're familiar with the screen templates that we're using where we can display colorimetric information. We're going to be focusing specifically on graphics during this session. One of the first graphics that we find of interest are reflectance curves. Now, if you're familiar with using a spectrophotometer, you know that the purpose of a spectrophotometer is to measure the reflectance of a sample. And from the reflectance, we generate what we call a reflectance curve, basically a set of numbers that are used to generate all of the color differences that we calculate within Datacolor TOOLS. So let's have a look at some reflectance curves to get you familiar with them. If you've attended one of our color science webinars, then you're also been introduced to reflectance curves, but we're going to show you a little bit more information about those to you today directly within Datacolor TOOLS. So first, how do we access the different graphics within the system? During one of our previous sessions, we discussed how you can modify a template by right-clicking within a section and choosing switch, and then you can choose a plot for viewing the graph or viewing the types of information that are of interest to you. Now that's more about how to change it within a template, but if you just want to open a plot, or open a graph, along our ribbon bars, we do have the plots menu. If you click there, you can get access to all of the plots that are available within Datacolor TOOLS. So let's have a look first at a curve plot called the %R curve. Now you'll notice that in our drop-down menu, we have %R and %T. R stands for reflectance, T stands for transmittance. So if you were working in a industry where you were interested in how light passes through a material, such as plastics or paint, or even working with liquid dye stuffs, then you might use % transmission curves, which again is a measure of how light passes through a material. Well, we're interested in a reflectance curve. So I'm going to click on the reflectance curve, and immediately my screen changes to show you just that. This is a reflectance curve, which again is a measure of how light reflects from the surface of a material. Along the bottom of the graph, we have our wavelength range, which is typically from 360 nanometers to a high of 700 nanometers. That changes based upon the type of instrument you're working with. Some will go across the range from 400 to 700 nanometers, some from 360 to 750. The primary area of interest, though, is 400 to 700 nanometers. Along the left-hand side will be a scale from 0 to 100% that represents how much light is reflected from the surface of a sample. So as we look at the shapes of the curve, we get a general idea of what the color is. Now my standard is currently a black. You'll see on the left-hand side, I have the standard name black that's highlighted, and that sample is represented by the dashed line across the bottom of the screen. If I hover my mouse on that line, you'll see the name also appears. It says black %R settings. Now, any standard that I have selected will show up with a black dashed line. This just happens to be a black shade as well, and the reflectance is quite low. You'll see it's all around 5% across the entire spectrum. The batch that I currently have highlighted, you'll see the name on the left-hand side is cyan. It has this distinctive hump in the blue area of the spectrum from about 460 to 480 nanometers. Again, if I hover the mouse over that, you'll see that the name also appears cyan. I'm going to click through various samples on the left-hand side so you get an idea of how those reflectance curves look. If I click on white, this represents a white tile. You'll see that the white tile has a very high reflectance, around 90%. And this is pretty consistent for the white tiles we use for calibration. And so with the black and the white, we establish the working range of the instrument. Other shapes of curves that you'll have, if we look at the gray curves, for example, pale gray is basically a flat line across the entire spectrum, but the total reflectance is only about 65% because it's a little bit darker than our light shade, than our white. If I go to medium gray, again, the curve drops down to about 30%. And if we look at our deep gray, much lower, again, below 10%. So we can learn from the height or the percent reflectance of the tile, how high it is on this graph, how light the shade is. The higher it is, the lighter it is. And then our distinct hues have different shapes to them. So we looked first at the cyan. If we look at a blue shade, up on my deep blue, we see it has a peak here around 400 nanometers to 420 nanometers and is very flat through the rest of the spectrum, indicating that it is indeed a blue. And we find a green. Let's see, there's my green. You'll find the peak shifts to the right where we've got our wavelength of maximum reflectance in the 500 to 520 range. And then I believe I have a yellow here. You'll see that curve shifts even further to the right. And now we're getting a lot of reflectance in the red region, but our eyes are responding to this peak reflectance curve here in the yellow area. And then we move on to a red. So every curve, every color has a distinct shaped curve. You know, so far we've been looking at samples that range from 0% to 100%. Now we know that some samples are fluorescent. Well, what does a fluorescent curve look like? If I choose my fluorescent whites, what we find is our curve disappears above the top of the scale because it's reflecting more than 100% of the light energy that strikes the sample. In order to see the entire curve, this is the first function we want to consider, is if I right click in the graph, you'll see there's an option that says auto scale. If I click on auto scale, the system automatically adjusts the scale to show me all of the reflectance points for the samples that I'm working with. In this case, I can still see the black along the bottom, and now I see with my white, I have a peak around 440 nanometers. And because this peak goes above 100%, it goes actually 115%, that tells me that this is a fluorescent sample. In this case, the fabric was processed with an optical brightening agent, or OBA, as a part of the dyeing process to give it this very specific peak, making the samples look whiter than they are. Now we also have fluorescent colors we deal with. I've got a few of those to look at. If I look at a neon orange or fluorescent orange, you see a very, very high peak above 170%, around 610 to 620 nanometers, again, indicating that it's fluorescent. Likewise, in neon green, you'll see the characteristic peak well above 100. Neon pink, the same way, and also with neon yellow. So reflectance curves are interesting in that they can show us how or what the data points were that were measured by the instrument. Well, how else can we use a reflectance curve? At this point, it's interesting to look at, but it doesn't really tell us a lot about the samples themselves. But there is one very particular way of using a reflectance curve that we find very interesting, and that is to determine whether or not two samples contain the same dyes. So let's set the stage with a scenario where I have an olive standard. And in this particular case, you'll see the olive standard on our graph is represented by the black dashed line. And we have gone through the lab dipping process and we've approved a sample, and I'm calling this olive approval. So you'll see that the red line here is the olive approval. Now it's not a perfect match to the black line, and that's fine. It's quite possible that our standard was a reactive dyed cotton, and then we're dyeing this sample on wool, for example. Maybe we've used acid dyes. Well, we would expect that acid dyes on wool would not give exactly the same curve as reactive dyes on cotton, and that's fine. Ultimately, what we were interested in with this particular olive submission was it acceptable? And we're going to say that yes, it was. So now let's say we move into the next case where we're going to receive our first of production. We would expect our first of production to be a pretty good match to our approval because the supplier should be using exactly the same dyes. So I'm going to use a technique in Datacolor Tools that allows me to swap the standard in the batch. So I'm going to make my approval my standard, And I'm going to choose my first of production. And now we see that, yes, even though the approval wasn't a really good match to the standard reflectance curve, now we see that the approval is indeed a very good match as far as the shape is concerned with my first of production, which is exactly what I would expect, because if they're using the same dyes, you're going to have a very similar shape to the curve. Now just for the moment, I'm going to close this, this reflectance graph. We're going to go back to our color difference screen. We're going to find our CMC template to show us the actual color differences. And I'm going to show just the current batch. And what we find is that the color difference, the delta E between the first production and the approval, is a 0.55 delta E. And that's not bad, right? If we have a production tolerance of 1 or even 0.8, then the supplier has done a good job. What we also notice is that that delta E is basically the same across all 3 light sources. And so we're satisfied and we give our first production and approval. So now the supplier moves on into regular production and we receive that first production, and we notice something very interesting is that now, rather than having consistent color differences in our 3 light sources, the numbers are very different. Sure, we have a really good close match in our primary light source, 0.16, but now look at our color difference in fluorescent and incandescent, 1.85 and 3.12. Well, what happened? Why are we having such a significant problem with the flare of the sample? The sample is flaring much redder than the original approved production. And this is where we can learn a little bit more from a reflectance curve. So I'm going to go back to my reflectance curve again. And what I find this time, let me switch to auto scale so we can zoom in a little bit. Now we see that the olive production does not match the approval very well with as far as the reflectance curves go. What we find is that it crosses several times, in this case 3 times. And the general rule, and this is something that your reflectance curves are very useful for, the general rule is if you have reflectance curves that cross 3 or more times, they're using different dyes. So what I could confidently do is go back to my supplier and ask why they changed the dyes once they moved into regular production, even though they had an approval on their first production. So this is just one way that you might find the reflectance curve to be useful, is to determine whether or not those samples have the same dyes, and also whether or not something's fluorescent, because as we said, if the reflectance data goes above 100%, then we know we have a fluorescent sample. Now, there are a couple of settings I want to show you for reflectance curves with regards to labels. If we click on our system menu along the top, you'll find in the center there are our defaults maintenance icons, and the first one here that I'm hovering on is for plot defaults. If I click on plot defaults, I'm given the opportunity to change various settings that affect how the graphs perform. If I choose my spectral curve plot, you'll see that I have 3 choices. I have the option for auto scale. If I check that, that simply means that each time I open the reflectance curve for a different color standard, it will automatically scale to show me the range from lowest to highest reflectance. Current batch limits the display to the current batch rather than to all batches. And show legend, which I will turn on, will actually give us the name and a legend on the graph itself. So if I choose OK, now what we find is on the right-hand side, you'll see our legend, and it shows us which colored lines correspond to which batch. The auto scale is also set, so our scale in this particular example goes from 2 to about 38%. Now I did have current batch turned on, but if I right click and turn that off, turn off current batch, you'll see that I can get all of the graphs on the screen at the same time, and it can be a little bit tedious to identify the sample that you're interested in looking at, and so that's why we typically have that current batch set as a default. One other thing that you can do to zoom in is if I use my mouse and I'm going to click and hold my left mouse button and click and drag a box around a section of the reflectance curve, when I release, you'll see that it zooms in on that section of the reflectance curve. And again, as I hover the mouse over any particular line, the name of that sample will appear. And there we go, all of first production. If I click on it, then that is also the line that will be selected for my color difference evaluation. If I want to go back to the original display, I right click and choose reset zoom, and it takes me back to my 0 to 100% or to my auto scale. So that's how they use a reflectance curve. Well, let's take a look now at some more uses of our color difference plot. We've seen this color difference plot before, and I'm going to choose a different standard here. Let's choose our arcade sample. I'm going to, rather than using the smaller graph on my lower left part of my template, I'm actually going to click on plots, go to color difference plot and select color difference. That will bring up for me a large version of that color difference plot. Now that's not the only way I can get there. One other shortcut, if I close that, is to simply double click on the graph that you're interested in looking at, and that will also automatically expand out. Now, the first thing we want to see has to do with the scaling. Notice that my pass-fail ellipse, in this case, fits nicely on the screen. I'm controlling this through a scaling function in my settings screen. And let's go back there again for a moment. If I click on System, click on my first default settings, plot defaults icon, and look for color difference plot, you'll see I have a few more options here. The one that I just mentioned to have to do with scaling is controlled by this option called fixed scale, where I have the fixed scale set to 2. That simply means that my graph will default to about 2 delta E CIE, which is sufficient for showing me all of the pass-fail graph and a little bit of space around that. I could choose auto scale, in which case the system would automatically scale in based upon how far away those samples are from the standard. And if all of your samples are really, really close, it may zoom in well into the pass region. And so the perspective is not as, in my experience, not as useful as using the fixed scale. We have some other options. I'm going to turn on show legend and show label, so you'll see how that affects our display. If I click OK there, you'll see that with show legend and show label, now our dots are replaced with letters, A, B, C, D, and so forth. And those correspond on the right-hand side of our graph to our legend, where we can see that sample A is 4365 and so forth. Also, as you hover over those letters, the name of that sample also appears. We're going to go back to our color difference plot defaults and turn off our show legend and our show label. And we're going to leave it on fixed scale. So the other useful features here in our graph, of course, if you hover the mouse over a particular batch, the name pops up. If you click on that particular batch, it does get a black circle around it, and that is now the name that's highlighted on the left, as well as the sample for which we are able to review our color difference data on our grid. A couple of other useful features here. If I want to zoom in to a particular area, just as I do with reflectance curves, I can click and draw a box around a certain region, and the software automatically zooms me into that region. If I want to reset to go back out, I simply right-click and choose Reset Zoom. One other function that you may choose to use involves using the right mouse button. If I click and hold the right mouse and then drag my mouse up or down, you'll see that it automatically zooms in. So this is another way that you can control your zoom in. But at this point, it keeps the standard at the center of my graph. When I'm using my right click and dragging the box, I can zoom into a certain area, and I'm not required to keep the standard at the center of the graph. So we'll right click and choose Reset Zoom again. Another useful feature is the ability to display this plot in different light sources. You'll see that I can switch from my primary to my secondary and tertiary light sources simply by clicking the tab. And what we may notice is that in some situations, the standard and or the batches will actually change position. In this particular case, we'll see that the arrow that represents the hue angle for this particular standard does indeed change significantly, and it moves into more of a yellowish red shade. So as this arrow is pointing down, that hue angle is in the blue-red quadrant. When I shift to A, it shifts up more towards the red-yellow quadrant. So there is probably a significantly noticeable flare for this standard. The other question, though, is whether or not the batches are flaring the same way. And I can qualitatively look at that, so I can say, well, yeah, they're all dull, and most of them are on the blue side. And when I click on the A tab, I see that there's some change there. So the graph only is going to give us more of a qualitative assessment, not a quantitative assessment. And for that, we want to go back to our color display grid and actually look at the data that's available to us. Now this is a CMC plot. If my standard has stored with it a different tolerance, as we discussed in one of our former sessions, then you can right click and you would see an additional tolerance formula available. We don't have one for this particular color, but if I choose my blue shade, what we'll find is that this blue does indeed have a CMC plot available to it, and we can see that information here, but it also has available in what we call an AI plot. And you'll notice, let me go back to my CMC graph, and we'll zoom in a little bit there. This particular CMC plot you'll see is very uniformly distributed, has the classic elliptical shape, but all of my batches are congregated in one area, And if I wanted to establish a quadrant type pass-fail program, we can do that with our AI tolerancing solution, again, which we reviewed in one of our previous sessions. But the advantage here is that when I right-click, I can actually choose that AI pass-fail region, and you'll see that all of my batches are now constrained to a certain area, and any batches that I receive in the other areas would fail, even if they might pass on CMC. So this, again, is a simple way of switching between the graphs for the different pass-fail tolerance programs that I have available to us. So that's our CMC plot. There are a couple of other very useful ones that we're going to look at. One question that we often have is, how do I know whether or not a switch to LED is going to be a problem for my organization? So let's say, for example, that I'm going to continue using D65 as my primary light source, but I'm interested in knowing what happens if I switch from fluorescent, cool white fluorescent FO2 to one of the CIE approved LED light sources. Well, let's first add in one of those LED light sources. I'm going to click on the Illuminate Observer icon here on my System menu. And on the right-hand side of the list are all the available illuminants that I have in my database. And I currently have a couple of the LEDs added to the system. Here's one called LED B2, which is what we think is going to be one of the more popular LED sources, but we want to know, how does it compare to my fluorescent? So I'm going to add that in, and I'm going to move it up one level so that it becomes the third light source on my list. And I'm going to simply click on OK. And that's now going to add in the LED light to my list. Now, what I would first see, just looking at the data, the numerical color differences, is whether or not those values are similar. So in this particular case, I'm looking at my blue shade. I find that for the DL, the numbers are very similar. The DC, they're very similar. The DH, very similar. So I could say, yeah, it looks like for this color, I'm not going to have much of a difference between LED and my cool white fluorescent. But I don't want to do this exercise for every single color that I'm working with. If I've got thousands of color standards, it's too tedious to look at the color difference data. I'd rather do this graphically. So let's go back and pull up a different shade. I'm going to go back to my black that I used originally for our reflectance curve analysis. Now, when we pull up the black, of course, we have really, really large color differences, as we would expect. There's a significant difference between neon yellow and black. But I can also use this as a way of evaluating the differences between D65 fluorescent and my new LED light source. And I'm going to do that with a very special plot. So if I go back to the plot menu under color difference, you'll see that I have one called multiple C-Lab illuminants. So multiple C-Lab illuminants. When I click that, I'm going to change one of my settings to show just the first 10 batches. I get a very interesting graph that has a number of lines on it. Well, each line represents a color that I have on my desktop: cyan, deep blue, deep gray, and so forth. Let me zoom in to this one here. If I hover my mouse over any particular point, I see that this blue line represents my cyan color, and the black box that I happen to be hovering on now is the representation of cyan in Illuminate A. If I move to another block, I see this is a representation of the LED light source. Here is the representation of the cool white fluorescent, and here is the representation of D65. So my question is, how does the sample change when I go from fluorescent to LED? And so here, qualitatively, I can say there's a significant shift into the blue-green region for cyan. So if I were to evaluate cyan and fluorescent and then look at that at LED, I would find that there's a significant shift. And I can qualitatively make this assessment for all of my samples just by looking at the shapes of the lines. For the orange, again, we see that D65, FO2, if I move up, here's LED and incandescent A. So there is some difference between fluorescent and LED, perhaps not as significant as it was for the cyan. For some other shades, let's zoom in here. This represents the red color. And for the red, here's D65, FO2 is here, and the LED is quite a bit different this time. So we know that this particular red is going to look a lot brighter and cleaner in my LED than it does in the cool white fluorescent. So this multiple C-Lab illuminant graph is an interesting way of evaluating how samples would change from one light source to another. Another very useful function for the multiple C-Lab illuminants is to, as we saw earlier with the reflectance curve, is to determine whether or not samples themselves will have different metamerism. So let me switch back to my original light sources. I'm simply going to remove the LED. I'll go back to D65 and fluorescent. I'm going to go to my olive shade that we tried working with earlier that showed the significant differences in the reflectance curves. And let's pull up those samples with our multiple C-Lab illuminants. So what we find here is pretty significant differences in the shapes of those lines. If we look at our approval, here it is, here's our first production. We find that for our first production, there's not a significant issue with flare compared to our approval. The lines are all very close together. But if we look at our ongoing production, we find there's a significant difference in the shapes of the shape of this line, indicating that there is indeed a significant difference in flare between those two samples. The other scenario where the multiple C-Lab illuminant plot is very useful is if I'm looking at a large number of samples. So I'm going to retrieve a different standard. Let's retrieve our beige string, and I'm going to retrieve some samples for that we've got in this database. Let's retrieve a large set of these samples. And this might represent a number of production lots from one supplier, or it might represent multiple lots from multiple suppliers. And we want to know whether or not they all have the same characteristic flare tendencies. In this case, once that data is retrieved, I'm seeing all the data at one time. And again, if I look at the general shape of all these lines, they are all basically the same. So I can confidently say that these samples are going to look good together when I put them in the garment, and I don't have to worry about when the light changes having one component flare in a different direction than the other component. Now, if I happen to have one of these samples that stood out as having a different direction, actually there is one here, and then if I look a little bit more closely, you'll see there's this one lone sample here, J-3011, that has a very different shape to the lines compared to all the others. So in this particular case, if this sample was evaluated in a light cabinet with some of the others, we would see that it would not change in the same direction as the others do. And we've been able to make this assessment by looking at a large number of samples at the same time. We've not had to look at each one individually at the colorimetric data. So again, this is the multiple C-Lab illuminant plot, one that I think you'll find is very useful. A few of the other plots we have on the system that if you were in production area, you might find interesting. We can look at the trend plot, where if we're trying to track how our samples are performing over time for the various color components, DL, DC, and DH, we can see that, and you would be able to notice very quickly whether or not you're trending in the wrong direction for your production samples. So those are some of the graphs that we have to work with. One of the other areas we want to look at is our color on-screen display, what we call our color patch that you'll see here in the lower right portion of my screen. Now, there are a few points to consider before you begin making any sort of assessment based upon the color on the screen. The first is that we have to know whether or not the color is accurate. The only way you're going to have accurate color on screen, or as accurate as possible, is to calibrate your monitor. Now, some monitors are more suited for color calibration than others. The Datacolor has worked with monitors from ISO, EIZO, the ISO Color Edge line of monitors, all calibrate very well. There are other good monitors on the market. We're not in a position to test all of them. So when we're asked for a particular model, we use the ISO monitors. If you need more information about that, please feel free and reach out to us and we can discuss specific models. But in order to calibrate the monitor, you will have to use a special device called a colorimeter, which is specifically designed for monitor calibration, and Datacolor does offer those. Our Spider line of products, you may be familiar with the Spider 3, 4, and 5, and the Spider 5 being the latest one that's compatible with the Datacolor Tools program. But once you've calibrated your monitor, then you're able to display color accurately on screen as long as that color is within gamut. Now, by being in gamut, I mean that some colors cannot actually be displayed accurately on a monitor. In other words, the absolute color is not going to be realistic and not lifelike. If you are doing color difference evaluation, so you're comparing a standard to a batch, then absolute color is not as critical because you're judging relative color difference. So let's go back to our olive sample that we had before, and you'll see the lower, at least on my system, this is a green shade, and depending upon the type of monitor you're working with, you might not see exactly the same color as me, and that is fine. I'm going to double click to expand this screen, And let me drag my standard out of the way so that you can see I do indeed have a standard and a sample on the screen. I'm going to switch which sample I'm using. I'm going to swap my standard back into position and look at my olive production as my sample. Now our olive production does appear to be a good match. This is being displayed on tiles. I'm going to switch my light source by right-clicking, bringing up a context menu, and you see that when I right-click, one of the choices I have is illuminant. If I click on A2 to display this in incandescent, it may not be readily apparent to you on your screen, again, depending upon the environment you're looking at this presentation in, but this sample definitely is much redder under my incandescent light source than it is under my primary light source. If I right-click again, choose illuminant, you'll see that there is an option for all illuminants, at which point I can display my sample in all three light sources. If you're able to discern the color differences on the screen, you'll see that in our secondary light source, which is fluorescent, is much brighter, much greener, and in my third light source, incandescent, the sample is much more red than my standard. When we're working with color on screen, we don't always like to have text on the screen, but in that case, you're not sure what the light source is that you're looking at. You can turn some information on simply again by right-clicking, choosing display environment, and we see that we can display various information. We can change the background color. I'm actually going to add in my illuminant name across the top. Now you can see D65, cool white fluorescent, and incandescent A. Some other options that you can choose with the color on screen display. I'm going to choose this color called Bauble, which is a little bit nicer display color. And here you can definitely see the color difference now in the lower right, how this sample flares when I go between my three light sources. But in this case, the standard and the batch are all flaring basically the same direction, so I don't have any unusual issues with metamerism. I'm going to double click in here again to expand out that window, and I'm going to switch back to a single light source by right clicking and choosing D65. Well, what we like to do with our color patch window is to make assessments of color differences. Let me turn off my other details since I don't need to see the light source. We like to make an assessment of color difference. For this particular bauble shade, if I go back to my color difference table, I can see the data there. I can see that the sample is dark and bright and blue, and I can see the number 0.55, but that may not mean a lot to you if you're not really familiar with using color difference data, the numerical data. And so in this case, the color difference graph does become a useful, the color patch window does become a useful tool for us to evaluate color differences. Again, I'm currently displaying those colors on tiles. We find that displaying on tile is not so realistic. So what we'd rather do is to actually display these colors on materials that correspond to the materials that I'm actually developing. So if I right click again to bring up my context menu, you'll see the next choice is substrate. And I have various choices from either applying a substrate to all of the objects or to various objects that are selected. I'm going to choose all the objects, and now I get some choices of types of materials that I want to use for display of my color. Let me choose the poplin. And what I find is now those samples are displayed in accurate color on fabrics. And I begin to work with what we consider a virtual light cabinet, and I can make more realistic assessments of whether or not that color difference is acceptable. So there are a lot of substrates available on a system when it's installed. More often than not, though, you're going to benefit from having your own substrates. So if you wanted to get your own substrates into the Datacolor TOOLS program, just give us a call. We can talk with you about what that process looks like. You'll see that I have a number of systems or a number of fabrics here by default, including yarn. If I choose yarn, I actually do indeed have those colors now displayed on skeins. You'll find that there are a lot of flexibility with how we display color on screen with Datacolor TOOLS. One of the choices I have is actually to display color on actual garments. So if I choose one of the garments in my system, now I can have a look at how the standard and batch compare on actual garments, because that's more of a real world assessment of color quality. Let me choose a slightly different garment there. We'll choose this one, and you'll see this is a top, and we can see whether or not that color difference really means whether or not it's significant when I look at it on fabrics or on garment. So the color patch window is very useful for displaying color on screen. So again, the conditions you have to keep in mind are that you need to work with a high quality monitor, such as an ISO monitor. You have to calibrate that monitor using the spider device. And also consideration is you need to be working in a dimly lit environment, because any lighting in the environment will affect your ability to discern color differences accurately. Now, where this really comes, really makes the most positive contribution to our color development process is in the ability to evaluate initial submissions from suppliers without having to see physical samples. So if I have a supplier who's equipped with a spectrophotometer and they are using the same standard as you're using and they measure their sample, they can send you that electronic data in the form of a QTX file. And then you can look at the digital data, the color difference data, and you can also look at the color on screen to make a decision as to whether or not they should make a correction before sending you the physical sample. You may find in your experience that generally your first submissions do indeed require correction. And rather than having to look at that physical sample to make that correction, you can look at the sample electronically, make the comments to the supplier so that they can try again. And then don't actually ask for a physical submission until you have something that you feel can be approved visually. And so that may mean you get to round 2 or round 3 much more quickly, even giving yourselves the opportunity for an additional round or avoiding a best can do type situation. So those again are some of the graphic capabilities we have in Datacolor Tools to supplement the tabular data for color differences. And using those all together, you can move quickly into an opportunity of a more digital workflow where you can improve your overall throughput and improve your overall quality. If you have any questions on the graphics, want some more information about that, certainly feel free and reach out to Datacolor. And we're always available to assist, and you can actually review the recordings again to get more pointers on how to use these graphic tools. So as we think about what's going to be happening next, when we look ahead for the next webinar, we are going to talk about sample measurement do's and don'ts, because all the data that we've been using really is not of much value if we can't measure samples repeatably. So we're going to be focusing on how to generate accurate reflectance data from the various materials that you might be dealing with, and also focusing on some of the mistakes that people commonly make when it comes to making sample measurements. If you don't make a good sample measurement, then you're not going to have reliable data. All right, Jen, we'll turn it back over to you then.
Yeah, thanks, Ken. That was really great. Tons of good tips. Really, really nice. I'm sure the listeners will find a lot of use out of that. So just a quick reminder, like Ken said, if you are interested to learn more, want to get some hands-on in-person training, be sure to check out the Academy portion of the Datacolor website, where you can find a list of classroom-style training courses listed there. On their website, we also have the Datacolor blog, where we share industry trends, as well as user tips like the ones that Ken has been given to us, but more in written style. So be sure to subscribe to our blogs. So thank you very much, Ken. I think that was another great session.
My pleasure, Jen.